Hello everyone. So today let's solve the problem matching reduction, right? So we are solving the problem basically on the matching, right? Graph that's based on the matching actually. So this is rated 2800, right? So this is fine actually. So let's see. You can just go through the question. Basically, this was asked in the educational code forces around 134, rated for the division 2. You can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. So this is completely based on the bipartite graph actually, and you have to know the bipartite graph, man. So let me tell you one thing. So I was asked the question in one of the famous companies that basically I was asked the question mainly on the bipartite graph itself. The first round, actually, I didn't know at that time what was bipartite graph. I knew the graph, I knew normal algorithms, this one, Floyd-Warshall, this one, Dijkstra's, Bellman-Ford, Kahan's for the topological sorting. These kind of things I knew, but I didn't know bipartite graph and I didn't know Dinnick's algorithm and push relabel, this one, push relabel, those kind of things, right? So I was mainly asked the first question on the bipartite graph itself. That was uh, mainly based on the flow, I believe, that included flow as well. I had to implement Dinnick's algorithm. I didn't know the algorithm at all. I tried solving with the BFS, but I was rejected. So first thing is you have to know the bipartite graph, and I insist you to know a bit on this one. The standard of question actually was pretty good. Uh, I felt really good. I was not able to solve. I did try with the BFS. I did try with the BFS, but the approach was actually wrong. Right? I did try with the BFS, but the approach was actually the guy did explain about the bipartite graph clearly, right? The interviewer was pretty much good actually. He explained every step what is bipartite graph and how it works actually and what you will try to do actually here. He did ask everything, but the implementation was wrong. I knew it because I didn't knew the concept this one and I didn't know certain algorithms as well. Yeah. So I insist you to go through certain this one flow algorithms, at least Dinnick's algorithm. Yeah. At least if you can skip certain things, but please do this one. How do I say? Please do go through the Dinnick's algorithm. Please do go through the Kahan's algorithm. You have to know to solve the topological sorting. And this one, Dijkstra's and the Bellman-Ford or the Floyd, you have to know at any cost, right? So there are some graph algorithms you cannot skip, right? So certain companies start with a graph actually. They start with a graph, right? It's based on the company, but if they start with a graph, usually certain problems have to be solved with certain algorithms only. Yeah, they can ask they can ask any question, they can ask any question, but knowing certain algorithms uh, will help you to think in the same way, right? So you can solve the this one problem in a easy way, right? Rather than struggling there in the interview, right? So that's what I wanted to say. Yep. Now, let's see what the question states here. So we are given a bipartite graph. Actually, what is bipartite graph? So we have solved the questions already on the bipartite graph. I haven't explained about the bipartite graph till now. Yeah. So I'll just take some time just to see the bipartite graph. It's been a time that I haven't solved actually the problems on the bipartite graph actually. Yeah, let's see. Recently, I had solved one question actually, bipartition actually that involved bipartition, the approach basically. But we haven't solved the one that involves bipartite graph, right? So let's see. So see here, a bipartite graph is a graph where vertices can be divided into two disjoint and independent sets. You can clearly see here we have two sets, and it can be divided into two disjoint, and so this is disjoint, right? And these are independent sets. You can clearly see here, such that every edge connects to a vertex in one set to the vertex in the another. So see here, one is connected to this one is connected to this one as well as this one. So every other vertex is connected here from the set A to set B. All the vertices are connected actually in simple terms. Yeah, such that every edge connects this one, a vertex in one set to the vertex in another. Right. So this is fine, I believe. Let's move on with the characteristics here. So two sets of the vertices. The vertices V are partitioned into two sets. Yeah, the vertition V are partitioned into two sets here, and often this one often labeled U and V such that U union B and U disjoint B, this one is equal to, they have given B and this one, right? So this is fine. Next, edges only between the sets. Edges only between the sets in the sense every edge connects one vertex from set U to the vertex from the set B. They have clearly mentioned in the diagram. You can just look into this diagram, right? So this is fine. Next, no edges within a set, meaning there are no edges that connect two vertices that both belong to the set U, or two vertices that belong to the set B. Yeah, you can clearly see here. Suppose if we consider this one as the set A, and if we consider this one as the set B, see here. So here nothing, no vertex is connected to one another here within the set A or within the set B. Set A is connected, the vertex from the set A is connected to the vertex from the set B, right? So no vertex in the set A is connected to one another. Same goes with the set B as well, right? So that's what they have said. In simple terms, they have said that no edges within a set, and two colorable. Two colorable, what it states here, a graph is bipartite if and only if it can be colored using the two colors. If it can be colored using just two colors, right? Such that no adjacent vertices share the same color. This is fine, I believe. The two sets U and V form the two color graph. Yeah, this is simple, man. And let's go with the example and properties as well. A graph is not bipartite if it contains an odd cycle. It is not bipartite if it contains the odd cycle, right? Cycle with odd number of vertices, basically. Yep. So this is fine. Graph with the even cycle length can be bipartite, and you have to remember this. Graph with a even cycle length can be bipartite, but a graph is not bipartite if it contains an odd cycle. Just try to remember this. And the final one here is a complete bipartite graph that is denoted by K of this one. M comma N is a bipartite graph where every vertex in the first set, this one with the M vertices is connected to the every vertex in the second set with the N vertices. The total number of the edges is nothing but M into N. The total number of edges is nothing but M into N. Yeah. So I hope now the concept of the bipartite graph is completely clear, right? The concept of bipartite is completely clear, right? So this is fine. Bipartite graph is completely clear, I believe. Yeah. Now let's move on with the question, man. Yeah. Just give me a second here. Just give me a second here. Yeah. We are given a bipartite graph. So suppose they have said that we have N1 and N2. N1 and N2. Yeah. So we have been given a bipartite graph N1 left and N2 right with the M edges. Suppose N1 consists of 3 and N2 consists of 3. Let's consider just for the sake of example. Yeah. So we can just go through the inputs later actually. Suppose this consists of the 3 edges, right? So yeah, let me write on this way. Yep. Uh, suppose we are given a bipartite graph N1 left, N2 right, and M edges. We have to process online queries. Online queries. So we have type 1 queries here. Type 1 is nothing but we have to remove. So we have to process the online queries, which consists of the type 1 here. Type 1. So here, what does it say? We have to remove the minimum vertices. We have to remove the minimum vertices to decrease maximum matching size. What we need to do here, we have to remove the minimum vertices. We have to remove the minimum vertices, right? So this is fine. We have to remove the minimum vertices to decrease maximum matching size. To decrease maximum matching size. So this is what we need to do to decrease maximum matching size. I'll just write here ms, right? So we have to what do we call? We have to remove the minimum vertices to decrease maximum matching size by exactly one. Maximum matching size by exactly one. By exactly one. Yeah. And we have to print the removed vertices and sum of the indices of a new maximum matching yeah, this is fine. So this is type 1 actually. And we have one more criteria called type 2. So what we have to do here, we have to print the matching chosen previously. We have to print matching that is chosen previously. That is chosen previously. I hope this is clear. That is chosen previously, right? So edges are numbered 1 to m. Edges are numbered from 1 to m. Queries must be answered one by one, right? So we have to flush after each answer. Just remember this one. As we're making use of the Java, we have to flush after each answer. Yeah. So this is the question mainly. What's the question here? We are given a bipartite graph. This one n1 So n1 left, n2 right with the m edges. In this case, 3 edges, right? So perfectly 3 edges. We have n1 3, n2 3, right? So this one, what do we call? We have to process the online queries. Type 1, which is basically we have to remove the minimum vertices to decrease the maximum matching size by exactly 1. Maximum matching size by exactly 1. That one you have to remember the criteria, right? And we have to print the removed vertices and the sum of the indices of a new maximum matching, right? So type 2, we have to print the matching chosen previously. We have to print the matching that is chosen previously. This is the type 2. And edges are numbered from 1 to m. Queries must be answered this one by one. Queries must be answered one by one. Yeah, so this is fine, I believe. Yep, let me delete this one. Let me come to the input output part. So see here. So this is nothing but the I'll just explain the input output. So here, this is nothing but the N1, right? So this is nothing but the N2, right? N1 set, which consists of the this one, 3 edges, and this one is nothing but the N2, which consists of the 4 edges, and this one is nothing but the M actually. Total we have M, which is 4 edges, and the queries we have been given here, 4 actually. Queries we have been given 4 actually, right? So this is fine. Yep, these are the edges and these are the queries actually. Yeah, queries, edges and the queries. Yep. Now queries are 1 to 1 to this one, and these are the edges, 2 to 2 actually. So we can just consider here 2 to 2. So 1 to 3, 2 to 1, and 3 to 4. I don't have to write this one, I believe. You guys know it, I believe, in my opinion. So this is fine. Uh, this example, the same example, let's consider for the this one. What do you call? Uh, for the approach as well. The output that we need to get here is 1 minus 4, 3. For the first query, for the second query 2, we have to get 2, 1, 2, right? For this one, for the third query, we have to get 1, 2, 2, and for the fourth query, we have to get 1, 2 actually. Yeah, for 1, 2, 1, 2 respectively, we have to get this one output 1 minus 4, 3, 2, 1, 2, 1, double 2, and 1, 2 respectively. Yep. So now we have idea on the input output as well along with the question. Let's do one thing. Let's quickly discuss the approach followed by the complexities, and then let's write the code, right? So first thing you have to know here is we will be going with a Dinix algorithm to solve this problem, right? Dinix algorithm along with the this one, Konix theorem. Just remember this one. We will be going with a Dinix algorithm along with the Konix theorem to solve this problem. Yeah, Konix theorem actually it is used to find the minimum vertex, right? So minimum vertex cover actually. So if you know the Konix theorem, it is used to find the this one minimum vertex cover in the bipartite graph. Yeah, you can just go through it. If you don't know, if you can just Google it, it's easier to understand. You can just go through this theorem actually. Yeah, so we will be making use of the Dinix algorithm along with the Konix theorem. Konix theorem is used to find the minimum vertex cover in the bipartite graph. Just remember this one. Yeah. So now let's move on with the this one. What do we call? Approach part actually. Now we have n1 3 and n2 4 and m is equal to 4 edges we have been given. Yeah. So m is equal to 4 edges we have been given. So m is nothing but the this one actually 4 edges. So this one n1 consists of the three this one vertex, and n2 consists of the 4 vertex or the nodes, right? So this one are edges and this is nothing but the queries and this is nothing but the queries. Let's move on with the approach, man. Yeah, let's move on with the first part here. So as I've said, we'll be making use of the Dinix algo along with the Konix theorem. And again, what is the why we are making use of the Konix theorem here? Konix theorem is used to find the minimum vertex cover in the bipartite graph, right? So that's easy. You can just go through it, man. Yeah. Now let's move on with the approach part. First step, what we will do, we will build a unit capacity flow network. We will build a unit capacity flow network. First, what we will do, we will build unit capacity flow network, right? Flow network, right? So what we will be doing here, let me tell you this one, just listen to this carefully. Each left vertex, right? So suppose this one, let me this one here. This one we have 3 actually, and this one we have 4 accordingly with the input I'm considering, right? So each this one, what do we call? We are considering the source here, right? Source left vertex actually. Each left vertex is nothing but it edges we are considering. It passes through the each right vertex, right? So source is nothing but the each left vertex. So edges that is passing through the left vertex to the right vertex, and right vertex is called as where the adjustment that is called as sink. We know that one, right? Capacity is one everywhere. Capacity equals one everywhere. Suppose I can just write it in this way. Yeah. So each, again, I'm telling, we are just building the capacity flow network source. We are building a unit capacity flow network source here. Each left vertex, nothing but the edges, right, passing through the each right vertex actually, that is known as sink. So the capacity will be equal to one everywhere. So we have to run the DNIC to get the maximum matching and the residual graph. So we have to run here DNICs, this one DNICs approach actually, or DNICs algorithm. Why? So we have to implement the DNIC here just to get the maximum matching and the this one maximum matching and residual graph, right? Maximum matching and residual graph. For the residual graph, let me write RG here. So this is fine. Yeah, simple one. Yep. So again, let me tell you this. We will be running the DNICs approach, or we'll be going with the DNICs implementation here just to get the maximum matching and the residual graph, right? So let's move on with the second step here. From the residual graph, we have got the residual graph from this one DNICs implementation. From the residual graph, we will run the DFS. We will run the DFS. So basically, DNICs implementation or the DNICs algorithm uses BFS as well as the DFS, right? So it uses DFS as well as the BFS if you know the algorithm. If you don't know the algorithm, you can just go through the graph place algorithm playlist and you can just go through the algo, right? From the residual graph, we will be running the DFS from the source, right? What we will do, we will run DFS from the source actually. From the source, over the edges with the remaining capacity, over the edges with the remaining capacity to find the minimum vertex cover, to find the minimum vertex cover, right? As I have mentioned, so we will be running the DFS, will be running the DFS from the source over edges with the remaining capacity to find the minimum vertex cover using, so as I have said, to find the minimum vertex cover, so within the DFS, so we will be making use of the conics theorem, right? Conics theorem is used to find the minimum vertex cover in the bipartite graph. In the bipartite graph. Yeah. So again, from the residual graph, we will be running the DFS from the source over the edges with the remaining capacity to find the minimum vertex cover via standard conics theorem method. Yeah. So left vertices not reachable and the right vertices reachable form the minimum vertex cover. Left vertices not reachable and the right vertices reachable from the minimum vertex cover. The code, what does the code do? Whatever the code that we'll be writing, basically the code should collect those cover vertices in array P in a specific order, right? Array P in a specific order. Whatever the variable it is, in cover vertices in array XYZ in a specific order. Whatever the variable name consider. So in array, it has to be in array. The code has to collect those cover vertices in the array XYZ in the specific order. Then what we will do, let me come to the third part. So I hope this part is completely clear, man. Let me delete this one actually. Let's move on with the third point here. Let's move on with the third point here. So listen to this carefully. We have to pick the vertices form. We have to pick the vertices from that particular cover one by one for each type one query, for each type one query. So what does that type one indicate here? So I have already explained type one, we have to remove the minimum vertices just to decrease the minimum matching size by exactly one. So again, we have to remove the minimum vertices to decrease minimum matching size by exactly one. And we have to print the removed vertices and the sum of indices of a new maximum matching, right? So that's what the type one indicate here, right? So see here, this one we have to pick the vertices from that cover one by one for each type 1 query. So each such removed vertex, what it does, it decreases the maximum matching by exactly 1. right? So that is the reason we are going with the Dinix as well as the Conics theorem, right? So this is how the DFS helps as well. Yep. So each such removed vertex decreases maximum matching by exactly one. When removing the vertex X, we also update the bookkeeping as well as the answer variable, right, in the code. So the printed sum equals the is equivalent to the indices of edges in the current matching, right? So in the current matching. In simple terms, we have to uh, pick the vertices here, or we have to pick the vertices. We have to pick the vertices from cover actually one by one. From cover one by one actually for each type one. For each type one here in this case. Yeah, this is fine. So the final part here would be for each type 1. The final part here would be actually we have to consider type 2 as well as type 2 as well. So for a type 2 query, so this occurs only after the type 1, right? After the completion of the type 1, type 2 occurs. Just remember this one. Yeah. The code prints for the type 2 query, the code prints the last chosen full matching. The code prints the last. What does the code do here? Code prints last chosen. So this code prints actually last chosen full matching. Last chosen full matching. So I'll just write it over here. Last chosen full matching actually. Yeah. So let me tell you this one again, type 1 and type 2. So the third point here is we will pick the vertices from the from that particular cover one by one for each type 1 query. When I say this, each such removed vertex decreases maximum matching by exactly one, right? So when removing the vertex X, suppose any vertex X, right? So we also update bookkeeping and answer variable so that the printed sum is equivalent to the indices of the edges in the current matching. So this is for the this one type 1 query. So when we write the code, you will understand this one even better. But before writing the code, you have to know what we are doing, right? So you have to know the approach with what we are going. So for the type 2 query, the code prints the last chosen full matching, meaning here size and the edge indices consistent with the answer previously print, right? So consistent with the answer that is previously not print, basically printed actually. Fine, right? So suppose let's consider this first example itself. Let me delete this one for now. We are having the idea, right, on that this one approach actually. Now let's consider this one. Let's try to implement the same. So using the example here, first type 1 removes the vertex minus 4. First type 1 removes the vertex minus 4, right? So this is fine. Minus 4 and the right vertex 4. Right vertex 4, right? So right vertex 4. This one actually. Yeah, this one. So this is fine. Now, so they have given n1 and edges, right? So 2 to so this one I can just consider here and this. Let me show you this one here. N1 as well as the n2, right? So this one, two, three. So we have only three edges. So this one we have four. From 2 to 2 we have. From 2 to 2 we have. This is fine. From 1 to 3 we have. From 1 to 3 we have. From 2 to 1 we have. This one from 2 to 1 we have. And from 3 to 4 we have. From 3 to 4 we have. So this is the bipartite graph actually. So this is the bipartite graph actually. This is fine. Yep. What they have said here, actually using the example accordingly with the approach that we discussed, the first type 1 removes the vertex 4. Vertex 4, right? Vertex 4. This will be removed actually first. Type 1. So this one. Yeah. So this one will be completely removed. So removed first, R1 removed first, right? So this will print actually 1. So this will print actually 1. So accordingly with the approach that we discussed, so first type this one first type 1 removes the vertex minus 4, nothing but the right vertex 4, it prints 1. So output 1 we have got here. Fine. Now what it does, minus 4, right? So then minus 4, so this is nothing but the index format and the 3. So this is nothing but the sum of matching this one matching edge indices, right? So this one we have got -4 and 3. -4 is nothing but the index format. We have to display the index format as well. We have to display the index format as well, right? So 1 2 3 4, so this one has to be -4, right? 1 2 3 4, this one has to be -4, and the 3 is nothing but the sum of the matching edge indices, sum of the matching edge indices. So here in this case we have to display -4 and 3 along with the 4. So this is what they have asked in the question. I hope this is clear, don't get confused. Yeah. Next, this one. Then let's go with the type 2. Type 2 just prints the matching edges consistent with the sum 3. Consistent with the sum 3. Consistent with the sum 3. And it goes on, right? So this is one of the simple, this one. So we have discussed for this one. Yeah, you can just consider in the same way for others as well. For the others as well, right? So this is fine, I believe. This is fine, I believe. Let me delete this one. So this is the approach that we will be going with. I showed you the simpler one. I showed you the simpler one just for the sake of understanding, man. So the same thing we'll be doing for the other this thing as well, right? Other queries. We have to process all the 4 queries accordingly with this one input, right? For the other queries also we'll be processing in the same way. Type 1, type 2. Yeah. So this is fine, I believe. So this will remain same. This it just remains same. All we have to do is we have to process query 1, query 2, query 3, and query 4. We have to consider type 1 and type 2 as I have explained, right? So for this, we have discussed that how we will be able to implement the Dinic as well as the Conics theorem as well, right? And again, the Conics theorem is used to this one. Dinic uses BFS and DFS, and whereas the Conics theorem, this one, it is used to find the minimum vertex cover in the bipartite graph. Just remember this one for now. Just remember this one along with the approach whatever we have discussed, right? So now, as we have complete idea on the approach, basically, as we have complete idea on the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would be because of square root of v into, so this one will be because of square root of v into e, because of square root of v into e, right? In the practice here, v is equal to n1 plus n2 plus 2, and e is nothing but it is equivalent to the big of n1 plus n2 plus m. So overall we can just go with big of square root of n1 plus n2 into m plus n1 plus n2, right? Which is dominated by the initial max flow, right? So we can just write here big of square root of v plus v into e, right? So each query is big of one, that is amortized, right? Output and small bookkeeping, right? So this one we have discussed on the approach. You can just go through the this one, go to that part of the video and just you can just check, right? So we'll be going with a bookkeeping bj, the variable name I said, and also the resulting variable, right? So that is fine, I believe. Now, what will be the space complexity? Overall space complexity would lead to big of n1 plus n2 plus m actually. So this is for the flow graph and the auxiliary arrays, right? So overall time complexity and the space complexity for the code that we'll be writing in the future would be big of a square root of v into e and big of n plus n1 plus n2 plus m respectively, right? So now we have, as we are completely familiar with the approach and the this one complexities, we are good to write the code. Let's start writing the code, right? So first thing here would be this one. What do you call? Uh, So let's go with the input output. I mean, so we'll be making use of the fast input and fast output, right? So let's import the input output package here. So I'll just go with input output stuff. And also we'll be making use of the different utilities. So let me go with what.util dot stuff. So this is fine, I believe. Yeah. Now let's do one thing. Let's quickly go with the this one. What do we call? Class actually. So I'll just go with public mm, class. So let me go with the solution here, right? So within the solution class, let's go with the all this one man. What do we call initialization part? So first I'll just go with the static mm, final, yeah, in n equals. So I'll just go with here 2 0 0 0 1 0. So this is the nothing but the base limit that is used for the arrays, right? So we can just say, or we can just call this one as the safer upper bound, right? So next, let's initialize some global integers, this one that is used across the method. So I'll just go with here static. So we'll be making use of actually n1, n2. Also, let's make use of the m for the edges, n1 and n2 for the this one set, this one and set 2, m for the edges, and let's go with the qq. So let's go with the total qq for the query. So total tot, and the numbers will be making use of s and t, source and sink actually, and also let me go with the count. Let's set this one to the 1. So this is fine. Next, let's go with the w nothing but w of I that stores the index of the forward edge in the e actually, right? So this one I'll just go with a static int. So this one w equals new int of this one n actually. This is fine. So we will be going with, we have to go with the so many text w, also the visited or the reachability and storing the vertices, those kind of things. So let me copy paste this one and make the necessary changes one. So let me copy this one entirely. So this one I'll just go with p, just go with id, say h current d as well as the answer, right? So let me change the variable names here, and I'll tell you for what purpose we'll be using this one, right? So we this one, so this is the visited or the reachability marker that is used in the this one helper method dfs2. So we will be going with the dfs as well as the bfs when we have to implement the this one dynamic algorithm, right? So Linux implementation, right? So we'll be using there. So next we will be going with the P actually. P, what is P actually? So this stores the vertices actually. Yeah, the minimum vertex cover vertices in a specific this one. What do we call? How do I say? In the specific order actually. Yeah. So this stores the vertices, the minimum vertex cover vertices in a specific order. Next, let's make use of the ID. ID of view basically maps the node ID in the flow graph, right? So this one I'll just go with a ID. So this is fine. Next, after ID, let me go with a bj. So bj is nothing but the bj of I equals 1 if the original edge I is currently part of the matching, right? If it is currently part of the matching bookkeeping actually. We have considered the bookkeeping itself, right? Bookkeeping actually. I have considered the variable bj. This is fine. Next, we have to go with the adjacency list, and we have to go with the current edge pointer for the Linux DFS optimization. Yeah. So and also we have to go with the distance levels that is used in the Linux BFS, and finally sum of indices currently selected. Yeah, selected matching edges, right? So these four things we have to go for the adjacency list. Let me go with the variable H, right? So this one has to be current actually, current edge pointer. So I'll just give here CUR current. So this will be distance levels, nothing but the D distance levels in the sense that is used in the DINIC BFS, right? So finally, let's go with the answer variable as discussed, right? So there are some of the things that I need to change here. So within this one, the size has to be n into 2. Yeah, size has to be n into 2. Again, in the for the ID also the size has to be n into 2. So this is fine, I believe. Next, for the adjacency list also, we have considered the variable h, right? So the size has to be n into 2. For the current edge pointer for the Linux DFS optimization, whatever we have used, current CUR variable, the size has to be n into 2 for this as well. And finally, for the distance level that we make use of in the Dynamic BFS, for that one, D actually, whatever the variable we have made use of D here. So for this one, also the size has to be n into 2. So this is fine. So let me come out of this one entirely. Now, let's go with the edge structure that is used for the adjacency list storage, right? Just to mimic the typical Dynamic implementation, right? So I'll just go with the static here, static. So this one has to be class edge. So this is fine, class edge. So let's go with the destination next pointer as well as the capacity. Capacity, we can just consider this one as value, right? So I'll just go with the destination next pointer nxt as well as the capacity, nothing but the value val, right? So this is fine. Now let me come out of this one entirely. Let's go with the edge pool, meaning so we need up to a few times n edges here. So I can just consider in this way. I hope this works actually. Let's see this one later. Edge. So this one has to work. Let's see. New edge of this one. N into 6 actually. N into 6. So this is fine. N into 6. Now, now let's go with the static initializer just to actually allocate the each edge object in the array, right? So let me go with static here. Within the static, let me go with a for loop. So this one has to be int I equals 0, I less than length of the e here. So this is fine. Let me go with a I plus plus. This is fine. Yep. Now e of I has to be equivalent to the new edge of this one. Yeah, this is fine, man. So let me come out of this one entirely. Now let's add the directed edge, nothing but x to y with a capacity z. If I is greater than 0, then we have to map the input edge I to the forward edge index. Yeah, for that, let me make use of the, or let's go with the add helper method. So this one will be static void add. So within the add, we need the parameters x, y, z, and I, right? X, y, z, and also I, right? I. So this is fine. So within the add, this one, let's set the endpoint of the forward edge. So this one will be e plus plus. So this one will be count dot 2. So this one, let me assign this one to the y, and then let's go with the, we have to chain it into the adjacency list of x, right? So I'll just go with the e of count here. This one, let's go with the next pointer. So this one, let me assign this one to the h of x. Yeah, let me scroll this a bit. Yeah, now this is fine. Now let's do one thing. Let's go with the this one, what do we call forward capacity. So this one has to be e of count dot val. So let me assign this one to the z, and let's go with the head that points to this particular edge, nothing but h of x here. So let me assign this one to the cnt count as well as the final one here. So just remember which edge corresponds to the original input edge I. For that one, let's write the simple if condition here. If I is greater than 0, then w of I, w of I can just assign this one to the count cnt, count cnt, right? So this is fine, I believe. Next, let's do one thing. Let's add the reverse edge y to x. So this one has to be e plus plus x. This one has to be count, right? Not the x actually. Yep. So this one destination, nothing but 2. Yeah, let me assign this one to the x. Yeah. Next, let's chain this one into the adjacency list of y. So this one has to be e of count dot nxt here, nothing but the next. Let me go with a h of y. So this is fine. Next we are left with a reverse capacity. We have to set that one initially to the 0, and also we have to head for the y that is updated, right? So let's go with the reverse capacity initially 0, right? So e of count that we have to initialize with 0. Sorry. So this one dot val equals 0, and also let me go with the h of y, and let me assign this one to the count. Yeah, let me come out of this one entirely. Now let's do one thing. Let's go with the Dinic BFS one. When I said Dinic BFS, so we have to go with the BFS to build the layer graph. If you know the Dinix algorithm, right? First, we will be making use of the BFS to build the layer graph, right? Then we have to return true if the sink is reachable. If the sink, the target one, the N1 and N2, the N2 side, if the sink is reachable, then we have to return true. So that is the reason we'll be making use of the BFS. Then let's see the DFS. We will be making use of BFS and DFS both in the Dinic actually. First, let's go with the BFS to build the layer graph. So I'll just go with here static boolean. Sorry, this one small letter boolean. Let me name this one BFS itself. Right. So within the BFS helper method, so I'll just go with the for here, and I equals s, I less than or equal to t, I plus plus. So this is fine. Now, we just have to initialize the level and current pointers for all nodes. So this one has to be d of I which is let me assign this one to the -1. D of I equals -1, and current of I, let me assign this one to the H of I. So this is fine. So let me come out of this one entirely. Now let's do one thing. Let's go with the Q for the BFS. BFS uses Q. We know this one, right? So I'll just go with the Q. So I'll just go with the integer here. So this is fine. So what happened here? Just give me a second. What happened here? This is not taking at all. Let me go with why this is considering like this. Eh? 1 second. So let me just give me a second here. Let me go with the Q again here. I'll just keep integer here. So I don't know what was happening there actually. So this one will be Q equals new. So this one will be linked list actually. Yeah, as we are making use of the. This is fine. Yep. Now let's do one thing. Let's start from the source, and also we have to mark the source level, right? Starting from the source, I'll just go with the q dot offer of s, and also let's mark the source level initially. So this one t of s. So initially, let's set this one to the 1. Now let's go with the standardized BFS loop while not of q dot is empty, right? So this is fine, I believe. So within the while loop, first thing, let me assign x to this one q dot poll. So this is fine. Yeah. Next thing here would be, let's go with the for loop. Let's iterate outgoing the this one outgoing edges basically. Sorry, let's iterate outgoing edges here. So this one has to be int I equals h of x. So this is fine. H of x and I not equal to basically 0, and finally I equals e of I, but the h's of I dot next and next we have considered, right? So this is fine. Yep. Now let's do one thing within the for loop. So let me assign y to e of I dot 2. So this is fine. Yep. Now let's go with a simple if condition one, meaning so we have to go with the edge with the leftover capacity and unvisited. Yeah. So this one has to be if this is simple. E of I dot val actually if it is greater than 0, and d of y if it is equal to -1, meaning unvisited, then we have to set the level as well as we have to enqueue. So if you know the BFS pretty well, we are just going with a pure BFS implementation, right? So this one has to be d of y. So all we have to do is we have to set the level and we have to enqueue, right? So this one will be d of x plus 1. So this one, I forgot mentioning equals here. This is fine. We are assigning this one to the d of x, nothing but we are setting the level here plus 1 as it starts from the 0. Again, the last step here is enqueuing. Enqueuing, let me make use of the offer operation again here. Let me pass the y. This is simple. So let me come out of this one entirely. Let me come out of this one entirely. All we have to do is we have to return d of t. That is, if we have to check whether d of t not equivalent to the -1, meaning we have to return whether sync was reached or not, right? So I'll just go with the return d of t not equal to -1. So this is fine, I believe. Yep. So let me come out of this one entirely. So this one is fine. So now let's go with the uh, this one, DFS actually. So Dinic uses both BFS and DFS. So we have successfully, what do we call? We have successfully built this one, built the layer graph using the BFS, right? So now what we have to do, we will be going with the Dinic DFS, or we'll be making use of the DFS, pushing up to the flow units from the node X, right? So actually we have to return the actual pushed flow mainly, right? So let's make use of the DFS for this. So I'll just go with the static void here. So not void actually, it has to be int. It has to return this one, actual pushed flow actually. Static int, it has to be int actually. This is fine. Let me go with the int x comma int flow here. So this is fine. So within the flow, so within the uh what do we call DFS function actually, helper method. So let's go with the reached sync. Let's go with the reached sync, nothing but which returns the flow. Also, let's go with the amount pushed so far from this call, right? So if x equals t, then let's return flow. Then if let me go with int now equals 0, int now equals 0. This is nothing but the amount pushed so far from this call, right? So let me go with a simple for loop here. For int I equals, so this one has to be current actually. Cur we have made use of variable, cur actually current of x. I not equal to 0, I equals e of I dot n xt, nothing but the next. So within this for loop, again, let me assign y to this one, e of this one I, destination nothing but the 2. This is fine. Let's write the simple if condition again. So we have to go with the level graph and check that whether it is having capacity, right? So this one if d of y, so I can just copy paste the same thing actually. Where is this if d of y? So we wrote the BFS, right? So 1 second. So within the BFS variant. So let's do one thing. Let's type this one actually. I thought we wrote this one. D of y, if it is equivalent to the d of x actually, then plus 1 and e of I val here, if it is greater than 0. So here we have to push recursively, right? So we will be going with the recursion, right? So we have to recurse here. So let me go with int z equals, let me go with the DFS of y. This is nothing but the recursive DFS. So I'll just go with the math.min here, math.min of e of I, math.min of e of I dot value. So this is fine. Also, I'll just go with a flow minus now, flow minus now. Yeah, so we are just pushing this one recursively. Next, let's accumulate the pushed amount, nothing but now equals now plus z. This is also fine. Next, let's go with the decreased forward capacity as well as the increased reverse capacity. For the decreased forward capacity, we can just go with the e of I here dot value equals e of I minus z. And for the increased reverse capacity, we will be going with e of I can just go with I XOR this one. What do we call? I XOR 1 actually. Dot value equals I XOR 1 dot value plus z or the z. So this is fine. So let me come out of this one entirely now. Now, if we have pushed the required flow, then we have to update the current and we have to break from there, right? So I'll just go with here if now equals flow, then all we have to do here is we have to set the current of x to I. This is fine. The final one is we have to break from here. So I'll just give the break keyword here. So let me come out of this one entirely. Now we are left with only one thing, the optimization part. If no flow is pushed here, if no flow pushed actually, then we have to mark the node unreachable in the future. So let's mark this one as -1. That would make sense actually. So this one will be if now equals 0, d of x. Let's set this one to the -1. Also, let's return here now and whatever. So this is fine, I believe. So we are just returning how much was pushed, how much flow was pushed actually. So let me come out of this one entirely now. So now let's go with one more DFS, man. One more DFS here. So why we will be going with another DFS function here? So let's go with, suppose let's consider DFS2 as the second DFS, right? Helper method name actually. DFS2, what it does, we have to explore the residual graph on the edges with a capacity that is greater than 0 from the node X, right? So that is marking reachable, right? Reachable nodes in the vertex V, right? So that's what we have to do. That's what we have to do. So for this, we'll be making use of one more helper method named DFS2 actually. I'll just go with void DFS2. So this is fine. So let me go with the X actually. Let me go with the parameter X. So here, let me set the V of X to the 1. So we are just marking this one as visited. So let me go with the for loop here. So this one will be int I equals 1. I, mm, I equals 1, or we have to go with the h of x. So let me go with the h of x. I believe h of x is the right thing. I not equal to 0. This is fine. Here we have to assign the I to e of I dot next. So this is fine. This one first, it has to be 1 or I. Let me leave it. If we get the error actually, then we can debug later actually. This is fine. So let's traverse only edges that still have the capacity, right? So how can we write this one in the form of code? Let's see. Mm, just give me a second here. We are just traversing only edges that still have capacity, right? So let's see the same. So let me this one to here. This is fine. How can I write that actually? Let me write the simple if condition here. Let's see. If actually e of I dot the value, if it is greater than 0, and suppose v of e of I, so this one I'll just consider destination nothing but the two variable we have considered. If it is equivalent to 0, then let me recurse here. Let's recurse dfs2 of, so we have to make use of e of I dot 2. So this is fine, I believe. Yep. So let me come out of this one entirely. Let me come out of this one entirely. Now let's go with the main method. Yeah. Now we are done with the this one dynamic actually BFS and DFS, right? So within the this one we are going with the, or we'll be going with the this one actually conics theorem as well to find the minimum vertex. So this one, how do I say, minimum vertex cover actually, right? So as it is related to the this one bipartite graph actually. So this is fine. With the fine, let me delete this one, and also let me include here throws input output exception. Yeah, this is fine, man. So within the main method, so let me go with the fast scanner and the print writer. So I'll just be going with a custom fast scanner here. Custom fast scanner. I'll just give sc equals new fast scanner. This is fine. And also let me go with the print writer out equals new. So let me go with the print writer of system dot out. System dot right. So this is the first input reader, and this is the first output writer. Right. So before this one, what do we call? We have to go with the number of left vertices and all. We have to this one. Do certain stuff that is related to the input output. So let me copy paste this one man entirely. So this one, this is completely customized fast scanner. I'll just when intense optimization is needed, I usually make use of this template actually. Right. So let me copy paste this one. This is purely related to the input output. We don't have to worry. This is nothing. This has nothing to do with the logic, the logical part actually. Just give me a second here. So I'll just come here. Let me paste this one over here, man. So this one, this is the simple fast scanner actually. This is related to the fast input actually. This one, input part actually, input output part in simple terms. So I can just go with any template, man. It doesn't matter. So I just wanted to make use of this template, so I have went with it. It has nothing to do with the logical part. Let's continue with the this one where we have left actually. Yep. Now let me do one thing. Let's go with the number of left vertices, number of right vertices, number of edges, as well as the number of queries. So here, this one, 3, 4, double, 3, double, 3, triple, 4, actually, whatever they have given. So this one, I'll just go with n1 equals sc, the variable, the fast scanner actually, fast scanner variable. I'll just go with the next and so this is fine, I believe. Yeah. So let me copy this one. Let me copy this one. Enter, enter, enter. So this one is fine. I'll just go with the N2. Let me go with the M as well. And let me go with the this one, double Q. Right, so this is fine. This remains same. See the variable from the fast scanner where we have used sc dot next, so this remains same. Will not be changing anything here. So this is fine. Next, let's go with the source index in the flow graph. So let me initialize this one to 0. Also, let me initialize t to this one n1 plus n2 plus 1 here. Right, so this is fine. All we are doing here is we are going with a sync index that is after all vertex nodes, right? So this is fine. S equals 0 is nothing but the source index in the flow graph. We know this one. This is fine. Now we have to read m edges and add them to the flow graph, right? So in simple terms, we have to map each original edge index I to the this one. What do we call that one? Uh, yeah, we have to map the each original edge index I to the forward edge. We can just call that one as forward edge, right? So this is fine. Let's go with a for loop here. I'll just go with for here. Sorry, 1 second. So this is fine. I'll just go with a for loop here. I equals 1. I less than or equal to n. Increment I. So within the for loop, what we will be doing, let's go with the left vertex index. Also, let's go with a right vertex index as well. So int x equals say dot next int. So this is fine. Also, y equals the same thing. So let me copy paste the same thing here for scanner variable sc dot next int. Yep. So the next thing what we'll be doing here, let me make use of the add helper method here. Add of x comma y plus 1. Y plus not 1 actually. We have to consider n1, right? The left side vertex actually. N1 comma 1. And finally, we have to go with the right. So we're just this one connecting the left x to the right actually. Y plus n1. Yep, with a capacity 1 actually. And what does I do here? Capacity 1 is fine. Y plus n1 is also fine. And left x to right, that is x is also fine. What does I do? I maps to the edge actually. I maps to the edge. That is the reason we have considered I as well. So this add is nothing but we are making use of the helper method. First helper method add that we have written this one here actually within the main method. So this is fine, I believe. This is fine, I believe. Yep. Now let me come out of this one entirely. This part for loop actually. Next, let's move on with the further things. Now we have to connect the source to every left vertex with a capacity 1. Also, we have to convert this one connect every right vertex to the sink with a capacity 1. These two things. For these two things, I'll just go with the two for loops. So I'll just go with for int I equals 1 I less than or equal to ni. Sorry, not ni, n1 we have considered n1 and n2, right? So I'll just go with I plus. Yeah. So let's do one thing. I'll just go with add of 0 comma I comma 1 comma 0. Yep. Let me do one thing. Let me copy this one entirely and let me paste it over here. This one will be int I equals 1, I less than or equal to n2 instead of the n1 and I plus plus. So we are just going with the add of uh let me go with the I here. So this is fine. I plus ni. This is also fine. I plus ni. This is fine. Let me go with the t as well here. T as well. 1 and 0. Yep, this is fine, man. Now let's do one thing. Yeah, let's move on with the further things. We have to run the dynamic now. So we have already written, implemented dynamic actually, BFS and the DFS helper method that we have written. So this one, DFS and the BFS also we have already written, right? BFS here, this one. Yeah, BFS and DFS we have already written. Now we have to run the this one. What do we call dynamic, right? So this is fine. So I'll just come here. Let me write simple while loop, while of BFS as well as the DFS, right? DFS of we have to pass S along with the N. This is fine, I believe. Yep. Now let's move on with the further things. Let's move on with the further things. After the maximum flow, we have to find the reachable vertices from the source in the residual graph. For that one, we have already written the DFS2 helper method, right? So I'll just call the DFS2 helper method over here. We have to start from the root, nothing but the 0. I'll just this one pass 0 here. This is simple. This is fine. right? So now let's do one thing. Just give me a second here. We have so much code left right here still. Yeah, we have to build the minimum vertex cover set, nothing but P using the classic bipartite cover from the residual, that is what do we call a reachability, right? Residual reachability. Yep. So in simple terms, left vertices not reachable and the right vertices that are reachable, that will be present in the minimum vertex cover, right? So that will be present in the minimum vertex cover. Let's go with a simple two for loops here. So this one will be int I equals 1, I less than or equal to n1, I plus plus. So this is fine. So within the for loop, so let me go with if v of I, if it is equal to 0 actually, if it is equal to 0, then p of mm, total. So this one, let me assign this one to the I. So left not reachable here. So this is the part of the cover. Let me go with the one more for loop. So let me copy paste the same thing and make the necessary changes. So this one has to be instead of the n1, let me change this one to the n2. So all other things remain same. So this one has to be if v of I plus n1, if v of I plus n1. So if it is equal to this one value instead of 0, if it is equal to the value 1, then so this one will be p of plus plus total. So this one has to be we have to assign this one to the I plus n1 instead of just I. Yeah, we are just going with a right reachable. So this is part of the cover as I've said, right? So now we have to determine which original edges are used in the found maximum matching. If forward edge capacity is exactly 0, then the edge was saturated, right? So this is the part of matching. This one we know from the what do we call approach actually. So let's write the simple for loop here. So this one for, so I'll just go with a I less than or equal to m. So go with this. So what am I doing here, man? So this is fine, I believe. Yeah, this is fine. So within the for loop, the first step, we have to go with the forward edge that has 0 remaining capacity here. So this one, let me write if this one E of W of I, E of W of I dot val, if it is equal to 0, if it is equal to 0, then let's accumulate its index into the answer sum. So this one has to be answer variable, right? Answer equals answer plus I. So this is fine. The next step would be id of E of W of I, W of I dot 2 actually, dot 2. So let's assign this one to the I. Also, let me copy paste the same thing here. ID of E of W of I. So instead of 2 here, let me go with the XOR man. So XOR here, instead of the 2, let me go with the 1 actually. Yeah, E of W of I. So this one XOR 1. So here, let me go with 2 actually. This is fine. So this one somewhere I have done something wrong. This one I have closed here itself. So this one, let me close it over here. Sorry, here actually. This is fine. We are just assigning this one to the I, right? So we have to map the left side node to the same edge index. So that's what we are doing here. So this one ID of E of W of I XOR 1 uh, to nothing but the destination. We are assigning this one to the I. So finally, we have to mark the edge I2 as active in the matching this one bookkeeping actually. So for the bookkeeping, we have made use of the variable bj. So this one has to be bj of I. So let me assign this one to the let me assign this one to the 1. Yeah, sorry man. Let me come out of this one entirely. Now we have to process. So finally we have come to the last but nothing but processing the queries online. Yeah, so this is huge again. So we have to type so many things. No worries. Still we are not done actually. We have to process the queries online one by one. Right. So this is fine. While I'll just go with the QQ. If it is greater than 0, QQ is the variable that we have made use of, right, for the queries actually. So first let's read the query type. We must read only after printing previous one, right? So query one, it it can be type 1 or the type 2 accordingly with the question, right? So that one, first let's read the query type actually. So I'll just go with op equals sc, a fast scanner variable. I'll just go with a next int, right? So this is fine. What if the query type, this one type 2 actually, if op equals 2, then we have already discussed a type 1 and type 2. You have to know by this time. We have already come to the coding part, that to at the ending part, right? So if you don't know, you can just go through that part of the video and you can just check the question. Actually, we have discussed about the type 1 and the type 2, right? So I'll just assign the num to 0 here. So this is fine. Here OP equals 2 in the sense we are just printing the last chosen matching, allowed only after the type 1, right? So type 2 is allowed only after the type 1. We know this one, right, from the question. So next what we will be doing here. So let's go with a for loop here. So this one, int I equals 1, I less than or equal to m. So let me increment I here. So this is fine. Next, let's count the currently marked matching edges. So this one has to be if bj of I, if it is equivalent to 1, then let me increment the number here. So this is fine. So let me come out of this one entirely. Now let's print the matching size, meaning here out dot, let me give println. So this is fine. This one has to be num. This one has to be num. So this is fine. So let me go with one more for loop here. One more for loop because we have to print the edge indices in the matching. So this one we have to print the this one edge indices as well in matching. So one more for loop. For loops everywhere, right? So this one has to be int I equals 1, I less than or equal to m. So this one has to be I plus plus. Yeah. If bj of I, if it is equal to 1, then let me go with the out dot print. Let me go with the out dot print I plus. So we have the space. So let me leave the space here. So this is fine. We're just printing the edge indices and matching, right? So this is fine. So let me come out of this one. So first let's go with the out dot println here. So this is fine. Out dot println. We have to flush because as the this one problem requires online interaction, right? So this one let's go with the out dot flusher, or you can just go with the out dot close as well, right? And then we have to skip from here. So not skip, actually continue keyword, right? So I'll just go with the continue keyword here. So let me come out of this one entirely. Now let's do one thing. So what if OP equals 1? So this we have written when OP equals 2 actually. So that one we have to perform only after the type 1, right? So if OP equals 1, meaning type 1, we have to remove one in this one, remove one vertex from previously computed cover P, right? So we know this one. We know this one already. We have discussed this one. So let me write this one. Int x equals P of total minus minus. So this is fine. uh, Initialization is fine. What if that particular vertex corresponds to an edge currently marked, this one currently marked as matched actually? Then how can we write this one? Then we can just remove that particular edges index from the sum, right? Also, we can just go with a, or also we can, after removing the edges index from the sum, we have to unmark the particular edge, unmark that edge, right? So let's write the simple if condition. These things actually, let's try to articulate in the form of code. So this one will be if bj of id of x actually, if it is equivalent to the 1, then what we should do, let me go with answer equals answer minus id of x. This is also fine. We are just removing that edges index from the sum. Finally we have to unmark the edge actually. Actually this one will be bj of id of x, actually id of x equals 0 equals 0. Next, let me come out of this one entirely, if condition actually. So if it's the right vertex, then we have to convert to the negative printing format, nothing but minus y, right? So that one we have to do. Then how can we write that one in the form of code? Let me write one more if condition here for it. So if fx is greater than n1, so then we have to mark this one x equals minus of uh, x minus n1, x minus n1, right? So this is fine, man. Now we removed one vertex actually. All we have to do is we have to print one here, so removing one vertex. Yep. Next, we have to print the removed vertex as well. Left vertex, we have to print positive. Right, we have to print negative. All we have to do is we have to this one pass x actually within the println. I'll just go with the out. Let me go with the println of we have to pass x here. This is fine. X is the variable we have considered, so we have to pass x. So finally, we have to print the sum of indices of edges and the same maximum matching. Right. So this one I'll just go with out dot println of, let me pass the answer variable, and finally we have to flush because we have to flush after each query answer, right? So there may be any query. So in our case, it was we were having the 4 queries, right? So if you remember, we have to go with the flush or close actually. I'll just go with the flush here. Finally, so we have to close the output right out. So let me go with again. Let me go with the flush or close. Here I'll just go with the close. This is fine. Yep. Now let's do one thing. We have already written this one, right? So somewhere I have brackets actually. One bracket I have used extra, I believe. So this is fine, man. Yep, this is fine. Now this is it for the code. So before checking the code with the different inputs actually, let me do one thing. Let me copy paste the signature starter template. Just give me a second here. I'll just come here. Let me paste this one over here. Now let me come to the question. Let me copy this one and let's see what's the answer that we get for this. I hope we get the correct answer. We have illegal start of expression, static class fast scanner. So this is correct itself, right? So what is the wrong thing here? Helper class. So this is just the helper class. This is fine. We are just going with a custom input, right? So line number 190. What's wrong here? Static class fast scanner. This is fine. One second. So what are the mistakes I have done here is, so let me come to the main method here. See in the line number 132, I have given ni instead of the n1. So let me consider this one n1. Actually, we are considering n1 and n2, right? So set A, set B, n1 and n2 respectively. Yeah. So this one is fine. Let me run this one still. This is fine. Let's correct certain things first. Everything step by step. Now here, come here. So this is fine. So we are checking here v of, oh, this one has to be actually v of I plus n1 within the square braces actually. Not v of I separate plus n1 whole, right? So this is I plus n1 as whole, right? So we are checking this one, which is equivalent, if it is equivalent to the 1 or not, right? So this one remains b plus plus total equals I plus n1. This is fine, I believe. Yep, this is fine. Now we are this one within this for loop. We are just marking which original edges are in the matching actually. It's fine. So I'll just come here. So let me make this one capital I instead of the small I. So this one has to be capital I. This is fine. So here, oh, this one I have misspelled here. This one has to be I less than or equal to M. While typing, I have included by mistake. I have included U, I believe, or mistyped actually. This is fine. Yep, this is also fine. Now, now if I run this, still static. What the heck is wrong? Just give me a second. So I have missed one bracket here, I believe. So I had closed this one over here. This one I removed. I had to close this one actually after for loop. I removed without any cause actually. I didn't add that one again. Didn't check it all, I believe. So here this one, let me add this one. So let me hit the run button now. Yeah, we are getting 13523. 1 second. 35. Yeah. I hope this works as well. Let me copy this one actually. We can have the multiple outputs, right? Yep, this is fine. So let me come here. Let me hit the submit button. Matching reduction. Let me paste and let me hit the submit button, man. Let's wait for some time. I hope this works for all the test cases, man. Is huge actually. Hmm, Mainly Linux implementation along with the connect theorem actually. Minimum vertex cover in the bipartite graph. Hmm, Linux is fine. This one connects theorem. This one here. Basically this part. Yeah, this is fine as well. Then we are processing the queries, right? So this, yeah, exactly. So you have to know the connect theorem as well as the Linux algo, right? To implement actually. So yeah, you can clearly see here the verdict that we got here is accepted, right? So this one in the toast also it is showing accepted. So whatever the code that we have written works absolutely correct here. Right. So this is fine, I believe. Again, we have went with a pure Dinic implementation along with the Conics theorem, right? So Conics theorem, what it does, Dinic uses BFS and DFS. We know that one, right? To find the maximum flow. So this is fine. And Conics theorem, basically, it is used to find the this one, what do we call minimum vertex cover in the bipartite graph. Yeah. So with a combination of it, both actually we have just solved this particular problem. This problem is completely based on the matching actually. Yeah, usually we call this one as graph matching problems. Yeah, this is fine, I believe. Yep, the time 4645 minutes. So this one we have given 8 seconds, I believe. Yeah, this is fine, man. Yep, this word itself indicates that this is based on the graph matching actually. This is fine. Yep, I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.